Alvikan Bharti with your mentor Abhilash Sarkar. Till now, we have solved some problem on the basis of the theorem, that is the Bernoulli's theorem. There we find that two things are always applicable for steady flow. If any fluid is flowing through duct in steady state or streamline flow, for ideal fluid is the equation of continuity where the flow rate, volume flow rate same at any point of time, and second, at any point of time the energy is conserved. That means the pressure energy, kinetic energy, and the potential energy with reference to any other reference line common to those point will be same. So with that we have solved some problem, and that is the Bernoulli's theorem. Now we will move to get some application part on the basis of this Bernoulli's theorem. The first of kind is the venturimeter. That is an instrument being made to find the flow rate when a fluid, that ideal fluid basically, is flowing through a duct and want to get the flow rate. So how can I do that? So the application venturimeter this is an application on the basis of Bernoulli's theorem. Okay. So what it does, this will measure the flow rate. What is the flow rate? Volume flow rate. Okay. So what the volume flow rate is denoted by Q, and that is equal to cross section into the velocity. So how come it is flow rate? Because if I say this is the cross section and the velocity, that means the distance traversed. If this is distance traversed in t time, then your velocity is x by t. So that cross section, this is the cross section into the distance, upon time. So that means this is nothing but cross section into the distance is equal to volume per time. So that means the rate of volume flow. Okay, so what we need, the Q, that is the volume flow rate, is equal to nothing but A into V, and that is a part when the steady flow we have learned, we find this is constant because this is the equation of continuity. So what we learned, at any point the cross section and the respective velocity at that point, if I multiply, thus numerically is same at any point of time throughout the flow. Whatever be the shape of the flow line, that doesn't matter, but this will be same always. Okay, so on that basis that venturimeter is working. Now initially I will take some time to draw the arrangement of the venturimeter, and then after I will go to the theory part or the formula establishment part basically. Okay, so this the central line of the arrangement. Give me some time, be patient, so that I can show you the better picture of that arrangement, how it is look like. Okay. Okay, now the cross section at this end is, let's say, A1. The velocity just below, because this will be the fluid column here, this will be the fluid column here. There is a difference of fluid column. Let's say this is denoted by H. From the center line up to this height, let's say this is H1. From the center line to this line, it is H2. The cross section is A1 here, velocity is V1 and pressure is P1. At the same, this point is equal to A2, V2 and P2. Okay, I am just considering just below this small tubes. This small tubes is and then fluid is flowing from this direction. Okay, the flow of direction is this one. So due to this flow, practically you will find the liquid which is flowing, or the fluid which is flowing, will cause it a column in this, the permanent rays of the basically this is for liquid. For gas you won't get any physical height difference because you cannot see it. So for liquid it is basically visible, and the liquid column in this small tube, this is very small tube, let's say, and of equal diameter, of equal cross section rather. So these are having a different fluid column, you can see, and with the top surface there is a difference H, and that the height from the center lines, because as it is a uniform, so we can assume that the mass flow rate of the total flow is concentrated on the center line of the arrangement, because it is very uniform against the center line, and so the mass flow rate will follow the center line, and the mass flow rate and the height from this center line to the column in this tube is H1 and that is H2, and respective the cross section of the bigger one is A1. Velocity at this point, if it is crossing just below it, is V1 you can assume, and this is P1 pressure at this point. Okay, because there must be pressure difference, so that's why the flow is happening. And the same in this cross section, if I take, okay, the two cross section here and here, accordingly these are the values. Okay, so now if I first see the this part of this, if this is the pressure 1 P1 here at the center line, this, and can also understand, so if it is a open end, open to atmosphere, the pressure head is P atmospheric. The same thing here also, the pressure will be P atmospheric, isn't it? Because this is open to atmosphere, the atmospheric pressure will act on the surface of the liquid in this small tubes. So at this point, if it is P1, so P1 is equal to, let's say, P atmosphere I am assuming as P0 plus rho, the density of the liquid flowing, and that will raise up to, so the what is the pressure in this part, so this is equal to rho g and H1, that we know. The static pressure we are equalizing, static pressure here is equal to the atmospheric plus the liquid column pressure up to this. Okay, because we know this will not depend on the shape and size, only the height of the liquid column just is falling to this, so pressure is equal to rho gh. Okay, this is first equation. Second equation, if I follow here, that will be the P2, this is equal to P0 at the top, and the liquid column is of height H2, so this is the case. Now what is P1 minus P2? P1 obviously more, because liquid is flowing this way, so P1 minus P2 will get, this will be cancelled out, rho g will be common, and this is equal to H1 minus H2. Okay, this is your, let's say, this is first equation, this is second equation, and this will be the third equation. Okay, Now this part is over according to the static flow. What we know about the steady flow? The equation of continuity is A1 V1 is equal to A2 V2. This will be your fourth equation. And fifth is you can apply the energy of conservation. But this is central line, is a horizontal line. If I take any reference from this, so this is the equal height you will get. So the static head, the potential energy with that reference frame, if I take this as a reference frame, from there the height is your potential energy is equal in these two parts. So that will can be nullified from the both sides. What else it is remaining? The pressure energy plus the kinetic energy, half rho kinetic energy per volume I am talking about, V1 square, that is equal to P2 at this point plus half rho V2 square. This will be your fifth equation. That also can be reduced up to P1 minus P2. P1 minus P2 is equal to P1 will come this side, this will go that side. So half into rho into V2 square minus V1 square. Fine. So now this is your sixth equation. Okay, this is your sixth equation. Now this and this, if we equalize, P1 minus P2 is this one, P1 minus P2 is this one. Now equalizing 3 and 6, what you will get? P1 minus, so this rho G H1 minus H2 is equal to half rho V2 square minus V1 square. Now here rho is not contributing anything. So ultimately what we find is equal to V2 square minus V1 square is equal to 2 will come this side, 2 G H1 minus H2. Okay, so this is the ultimate equation. I will rub this part. Only I will keep these two things, this one and this one. Now, what is H1 minus H2? Is H, because if you deduct H1 from H2 from H1, you will get this much only. So we can put this, because why I am putting H? Because this is measurable. You can measure physically by keeping some scale, and you can measure physically. So this can be easily available. This you know as per the standard. So you can get the difference of this one. So this is your seventh equation. Okay. Now from there, what you can find? If I say V1 is equal to A2 by A1 into V2. Okay. This is your eighth equation. This you can replace here. So replacing V1 from eighth equation. What you will find? V2 square minus V1 is equal to A2 square by A1 square into V2 square again is equal to 2GH. Okay. So V2 square can get common, V2 square 1 minus A2 square by A1 square is equal to 2GH. So V2 square is equal to, you can put A1 square up into 2GH divided by A1 square minus A2 square. Now V2 is equal to under root of 2GH upon A1 square minus A2 square, and this A1 will come outside. Okay, fine. This is you understand. So the similarly, if I want to represent it in form of V1, this is V2. So what will be your V1? It is A2 by A1 into V2. So you can, if I can put A2 by A1 will be considered, only difference you will get A2 into the other thing will be same, 2GH by A1 square minus A2 square. This will be your V1. So for V1 it will be A2, for V2 it will be A1. Now volume flow rate Q is equal to what? A1 V1 at this point or A2 V2 at this point. Both are same. So if I put V1 value here, so A1 into V1 is equal to A2, so A1 it will come, and along with that 2GH upon A1 square minus A2 square will come, or otherwise if I put A2 into V2, that will give the same result. Okay, 2GH by A1 square minus A2 square. Fine. So ultimately what you will find, volume flow rate is A1 A2, the cross section, multiplication of this cross section, 2GH, that value you know, H, A1 A square is, you can measure because you know your instrument, so you know the diameter of this part, you can measure it, so you can put this value. Once you will get H difference after the flow is established and it is become a steady flow, you will get a definite value of H. So if you put that, you will get the flow rate through this venturimeter. Understand? So by this you can find the volume flow rate. Okay, now if somebody has to calculate mass flow rate, so mass flow rate is equal to volume flow rate into the density, isn't it? Mass is equal to volume into density. So density you know for the liquid is flowing, it is incompressible, you can say. So you can take the standard density and then density, if you multiply, this will become A1 A2 into 2GH by A1 square minus A2 square. Fine. So these are the equation that will help you for this application. So now we will do some problem solving, do some sum, so that thing will be more clear. Okay, maybe one or two. So let me take some example. The speed of water at x, I will show the drawing. Let me write the problem first. X is a point, is 30 centimeter per second. Find the speed of water at y if difference in height heights of two columns of water is 2 centimeter. So the arrangement is similar to that venturimeter. Okay, so there is a column here, this point is x. Okay, this is done, this is being reduced, and then further this part here also some column is there, then further it has increased. Okay, so now these are the equal diameter duct. Okay, fine. So this is open ended, So this is the liquid column here. So now okay, now liquid column is there. This height difference is given as 2 centimeter. Cross section here is A2. This is A1. The velocity here given as V1 is equal to at x. This is x, and this is point y. Okay, at this point. So that Vx at point Vx is equal to 30 centimeter per second. Okay. So now we have to go from the basic thing. A1, A2 is not given. Fine. So from this is V1 given, A1, A2 not given. So what we will do? Let's say A1 V1 is equal to A2 V2. That formula of continuity you can use. So V1 is equal to given as 30. So that means V2 is equal to A1 by A2 into 30. So this is the, and these all are in CGS. Okay, so we'll go with that. This is 2 centimeter column difference. H is equal to 2 centimeter. Now if I use the volume, that velocity formula, that velocity is equal to V2 is equal to A1 into 2gh upon A1 square minus A2 square. Fine. So if I take A2 common out of it, so this will be A1 by A2 into A1 by A2, or else V1 is known. Let me take V1, so this will be A2. So H is known, so this is V1. So if I take A1 common, so A2 by A1 will be there, and this will be 2g, H is equal to 2, 1 minus A2 by A1. This is whole square. Okay. So V1 value we know. So if I know the V1 value, the rest of the thing can be calculated. V1, if I take 30 is equal to A2 by A1. Yes, A2 by A1, if I square it up, so this will go there, A1 by A2. So ultimately this is 2gh at the top, into below it is A1 by A2 whole square minus 1. So from there you can calculate A1 by A2 whole square minus 1, that is equal to 2g means 1, because this is centimeter per square, so then we can take 1000. G value in CGS is equal to almost 981 gram per centimeter per second square. So centimeter, that is approximation. I am taking 10 to the power 3 centimeter per second for calculation sake. So we will take 10 to the power 3 for G. H is equal to 2 centimeter divided by 30 means 9 into 10 square. 30 square means 9 into 10 square. So this will cut. This will be 10, and this will ultimately how much? 2 to the 4, 40 by 9. 40 by 9. So A2 by A1, A1 by A2 is equal to, that will go that side, 49 by 9 under root, that means 7 by 3. Ultimately A1 by A2 is equal to 7 by 3. Now if this is the case, we'll find A1 by A2, 7 by 3. If we put here, we'll get V2. This is equal to A1 by A2 means 7 by 3 into 30. So that means 70. V2 is 70. Velocity we can find here. So now once velocity is there, what the speed of water at x is equal to this, find the speed of water at y. So this is the speed of water at v. Okay, understand my point. What I use? I use the this continuity equation and the velocity equation, that we from there a1 by a2 we find. Okay, so this way the velocity will be this will be centimeter per second at Vy, not V2 exactly, this is Vy. Okay, so move on to the next problem. Number 2. The area of cross section of wide and narrow portions of the tube are 5 centimeter square and 1 centimeter square respectively. The rate of flow of water through the tube is 500 centimeter cube per second. Find the difference in heights or heights of two columns. So the arrangement is, this is kind of manometer, I can say. This is kind of manometer that is being installed, YouTube manometer. That arrangement we have seen earlier also. In flow path we can use this kind of arrangement, and from the difference in the liquid column, this liquid is of a different density, okay, that can be kept below and having more density than the fluid it is flowing inside the duct. Okay, this is a complete arrangement. This is a kind of manometer, you can say. So this height difference can be measured, and now in this case it is given as the wide range, the narrower portion is 5 cm, the cross section here it is 5 cm square, and there it is 1 cm square. It is given. So it is the rate of flow through which the rate of flow is given is 500 centimeter cube per second. The difference in height, so this height you have to find. So this is also based on the same venturimeter. This is kind of manometer, but this principle is same, because if I say this is the center line, from there you will get the same equation, the pressure energy, the static head energy you can find, and here also the continuity equation can be used. So the cross section is there. So A1 V1, the continuity A1 V1 is equal to A2 V2. Straight away you can use cross section area is 5. V1, let's say this is at this point is equal to V1, you can assume, and this is equal to 1 into the velocity V2. So what do you find? V2 is equal to 5 times of V1. That is your first equation. And as Q is given, Q is equal to A1 V1 and A2 V2. That must be same. And if we assume both cases, so if we equalize this 500, and that is centimeter cube per second, the units are same. So what you want to find? This is V1 if you want to find. So 500 upon your cross section is 5. So V1 is 100 centimeter per second. You need not to have this equation, because from this equation also you can use equalizing this equal to cross section A. So this your V2 is equal to 500 centimeter per second. The both can be find. So you need not to have this equation. From this one equation you can find both the velocities. Now once you get the velocity, what are the things? How will you find? So velocity is equal to nothing but A2 into under root of 2gh by A1 square minus A2 square. So V1 you know, V1 you can put 100, and A2 is equal to this area 1, and under root of 2 g is equal to you can take 10 to the 2 for sake of calculation, and height h difference, this is equal to 5 square minus 1 square 25, 24. Okay, so this will be 12. So we have to anyhow you have to do square. So this 10 cube into h is equal to 12 square, 12 into 10 to the power 4 will come this side, because this will be squared up. So this will cut. H is equal to 12 into 10, that is equal to 120 centimeter will be the answer. Understand? So there are stop here. This is ending of this application of Venturimeter and few sum that is related to the Venturimeter, and I will proceed to the next theorem from the next classes. This is based on the fluid dynamics only. I have not still completed fluid dynamics. Few more things are there to discuss, and then after I will move on to new subject, and this time I will take up a mathematics subjects, because alternatively we are moving physics and mathematics. So this time I will start new chapter on mathematics. Okay, so thank you for now.